In this chapter, we've talked a lot about polynomial functions up to this point, and now we're actually going to move into talking about rational functions. So first, let's talk about what a rational function is. A rational function is a function whose rule is the quotient of two polynomials. So as you can see, that's why we start with talking about polynomial functions first, and now we're moving into talking about rational functions, which is the quotient of two polynomials. So you can represent it this way. H of x would be a rational function if f of x is a polynomial and g of x is a polynomial. Now the domain of rational functions, we've talked about the domain generally for any function, is going to be all real numbers with the exceptions of when you have square roots and denominators. Now since you don't have any square roots when you're talking about polynomials, all of the domain restrictions are going to come from the denominator. So the domain of rational functions is the set of all real numbers that are not zeros of the denominator, or in other words, don't make the denominator equal to 0. Take a look at example 1. F of x equals 1 over x squared. You're asked to find the domain, so the only domain restriction here is what's in the denominator. So you want to set the denominator equal to 0, and this is what cannot be in the domain. So setting this equal to 0 and solving, we get x equals 0. So the domain is going to be all real numbers except x cannot equal 0. That's the one restriction on the domain. Look at the next one. We have x squared plus 3x plus 1 all over x squared minus x minus 6. So again, to find the domain, you just want to figure out what's going to make that denominator equal to 0. So take that denominator, set it equal to 0, and solve. This looks like it's factorable. So x minus 3 times x plus 2 equals 0. Set each equal to 0, we have x equals 3 and negative 2. So the domain is going to be all real numbers except for 3 and negative 2. So we've talked about the domain. How do you find the domain of a rational function? It has to do with the denominators. Anything that makes the denominator equal to 0 is not going to be in the domain of the rational function. Now let's talk about intercepts. So in a rational function, the x-intercepts of the graph are going to be the ones that occur in the numerator but not in the denominator. So it's anything that makes the numerator equal to 0 but not the denominator. So it can't make the denominator 0 because it would then not be in the domain, but it's anything that makes the numerator equal to 0, which means the entire function is equal to 0, which means it is an intercept, an x-intercept of that rational function. The y-intercept, on the other hand, is when x equals 0, so you would just plug in 0 for x, and then solve and get your y value, and that will give you the y-intercept. Let's do some examples with intercepts. F of x equals x squared minus x minus 2 all over x minus 1. So to find intercepts, you want to see what makes the numerator equal to 0. So take x squared minus x minus 2, set it equal to 0. And we try to factor this if we can. It looks like it's factorable. So x minus 2, x plus 1, which means x equals 2, and negative 1. The only other thing you want to check is to see whether or not either of those make the denominator equal to 0. In this case, it does not, so 2 minus 1 gives you 1. Negative 1 minus 1 gives you negative 2. Alright, so those are your x-intercepts. The y-intercept is when you set x equal to 0. So we take our function and we plug in 0 anywhere we see x. So we have 0 squared minus 0 minus 2 all over 0 minus 1. That ends up being negative 2 over negative 1, which is equal to positive 2. And so our y-intercept for this graph is going to be at positive 2. Alright, the next concept we're going to talk about is continuity. So a continuous graph does not have any breaks or holes in the graph. A graph of a rational function has breaks or holes in the graph where it is undefined, causing it to have a discontinuity. Now, it is undefined, for example, when the denominator is equal to 0, right? Those places that are not in the domain, the function is undefined, and so there would be some sort of a break or a hole in the graph. Now, graphically, just so you can visually see what this looks like, this is an example of a continuous function. Here's an example of a discontinuous function. One easy way to determine whether or not a function is continuous is, are you able to draw the entire graph of that function without lifting your pencil? That's one way to think about it. It's a continuous function if you can. It's a discontinuous function if you cannot. Now, we're going to talk about two types of discontinuity that you may see. So you will have breaks in the graph at all points where the function is undefined. Now, a rational function has a vertical asymptote at a certain point if c is a 0 of the denominator and is not a 0 of the numerator. So any value that makes the denominator equal to 0, but not the numerator equal to 0, that's going to be a vertical asymptote. On the other hand, if there is a value that is a 0 of both the numerator and the denominator, we call that a hole. And those are the two types of breaks that you can have in a rational function. So in both cases, you'll notice that the denominator is equal to 0. But in one case, the numerator is not 0. In the other case, the numerator is also 0. So either you have a vertical asymptote or a hole. Take a look at example 4. F of x equals x squared minus 4 all over x minus 2. So we can factor as much as we can first. We have x plus 2x minus 2 in the numerator over x minus 2. Now you're looking for vertical asymptotes and holes. So look at the denominator, and we have an x minus 2. Now we set that equal to 0, and we know that x equals 2. Now because this shows up in both the numerator and the denominator, we know that this is going to be a hole at x equals 2. All right, let's look at the next one. F of x equals x squared minus 9 over x plus 3x minus 4. Looks like we can factor that numerator. It becomes x plus 3x minus 3. And now we look at the denominator. We have x plus 3 equals 0. Now we know that we see the x plus 3 in the numerator as well, which means that there is going to be a hole at x equals negative 3. We also have x minus 4 in the denominator. Set that equal to 0 and solve. Now because x minus 4 is not in the numerator and it's only in the denominator, that means that we have a vertical asymptote at x equals 4. All right, so vertical asymptotes are where you have anything that makes just the denominator equal to 0. And holes are where you have both the numerator and denominator equal to 0, something that shows up in both numerator and denominator. The last part of rational functions we'll go over today are horizontal asymptotes. Now, horizontal asymptotes, really what we're talking about is the end behavior of the function. What happens on the far end of the graph? What does it look like? If you were to zoom out really, really far, what does the graph look like? So the way we determine the horizontal asymptotes is we compare the degree of the numerator and the degree of the denominator. We're going to call the degree of the numerator n and the degree of the denominator k. So if n is less than k, then the x-axis is the horizontal asymptote, so y equals 0. So for example, here we have 3x squared plus 4 over x cubed minus 1. Right away you know that the horizontal asymptote of this function is y equals 0. Now if the degrees are equal to each other, so if n equals k, then the line y equals a over c is the horizontal asymptote. Now where did this a and c come from? Well, if you look back at the function f of x, you'll see that a is the leading coefficient of the numerator and c is the leading coefficient of the denominator. So you would divide the leading coefficients, and that will give you y equals, that number is the horizontal asymptote. So here's an example, 3x minus 2 over 4x plus 1. this has a horizontal asymptote at y equals 3/4. In the last case, if the degree of the numerator is larger than the degree of the denominator, then there is no horizontal asymptote. In fact, what you end up having is a slant asymptote. And here's an example, 4x squared minus 1 over 2x plus 5. And the way you figure out what the slant asymptote is you actually have to do polynomial division, which we've done before. And so you would divide those polynomials, and whatever the quotient is will give you the slant asymptote. All right, this last part here is just a summary of everything that we just talked about today. There's a lot, so just as for those of you who are more visual with a chart, and that might be more helpful to organize kind of all the different pieces of information from today, this is what it is. So how do you find the x-intercepts? It makes the numerator 0 and the denominator is not 0. The y-intercept is when you set x equal to 0. To find any wholes, it's something that makes both the numerator and the denominator equal to 0. Vertical asymptotes is something that makes just the denominator equal to 0. So the numerator is not 0, but the denominator is. And then horizontal asymptotes, you compare the degree of the numerator and the degree of the denominator. If n is less than k, horizontal asymptote is y equals 0. If n is equal to k, y is equal to a divided by c, so those are the leading coefficients. And if n is greater than k, then you have a slant asymptote, and to find that slant asymptote, you will have to do polynomial division. And that's the summary of all the different parts of the rational function that you're going to have to find. Next time we will be talking about how you go about graphing rational functions after you've found all these pieces of information.